Okay, we are still continuing with discussion on assembly language programming, and ARM processor is the example we have taken. We have looked at some instruction formats, DP and DT. DP is data processing, DT is data transfer. We have seen how instructions are internally represented for these instructions in the machine. And we look at other two formats also, branch and SWI. So within these instructions, there are constants, and we are trying to understand what is the range of values that's possible. Okay, whether the numbers or constants are signed or unsigned, it depends upon the instruction, and we will see examples of these. The addresses for memory which are provided, are they absolute or relative? And are we making addresses byte addresses or word addresses? So as we understand this, these questions will be getting cleared more and more. So let's recollect the deep set of DP instructions or data processing instructions like add, subtract, compare, and so on. So a 32-bit instruction is divided into various fields represented by the numbers shown here. Let me turn the laser pointer on. Yeah, these numbers represent width of the field. Okay, particularly this field of 2 bits is important. This basically represents, this is F stands for format. So for DP instruction, format for F field is 00. It's 00 for some other groups of instruction, because a large number of instructions have been packed, and therefore as we have seen that some instructions have little tedious kind of or weird kind of encoding. So therefore F is 00 for some other groups of instructions also, but primarily F00 represents DP instructions. Now RD is the destination register. Okay, 4-bit specify which register is the destination. Rn is the first operand, and operand 2, which is the largest field, is the second operand.
Excuse me, sir.
Yeah.
So are you sharing screen?
Sorry?
Are you sharing screen?
Yes, are you not able to see?
No, sir, we are able to see.
We are able to see.
It might be problem at his end.
Visible.
Yes, sir.
Let me-
I am able to see.
Let me unshare and share it again. So possibly it might work for everyone. Are you able to see? Is everyone able to see the screen now?
Yes, sir.
Okay, good. Okay, so I was talking about different fields. F field is for the format. OPC is the opcode. So 4 bits means you can specify 16 different instructions, add, subtract, and so on. There is a list of 16. We'll come to that at some point of time. And RD is a register field which specifies the destination register. RN is the first operand, which is always a register. The second operand can be a constant or immediate or a register. Okay, so the two options are shown here. It could be either an 8-bit unsigned constant, which can possibly be rotated by this rotation specification, or it could be a register, a 4-bit field specifies that, and a shift field which specifies in which manner to shift and how much to shift. Okay, the distinction between these two, or the choice of these two, is indicated by the I field or the immediate field. 0 for register and 1 for immediate. Okay, now the shift amount is shift type and amount is specified in these 8 bits, where 2 bits mentioned as type specify which type of shift it is. It is logical shift left, logical shift right, arithmetic shift right, or rotate. Okay, the amount of shift could be again a constant. In this case, a 5-bit constant specifying anything from 0 to 31. And alternatively, the contents of register specify the shift amount. Okay, and this particular bit specifies which of the two cases it is. Now, in the second case, this bit is 0 always. And if you put a 1 here, then it opens the space for other groups of instructions. And multiply group of instruction is one group. So in this part, which is just left to RM, that is these 4 bits. Okay, 2 bits of type, and this bit on the left, this bit on the right. These 4 bit, if this pattern is 1001, we get to the multiply group of instruction. Okay, so format is still 00. It has 3 registers involved: destination, and Rn is the first operand, first multiplicand. Rm you can take as the multiplier. Rs is required for multiply accumulate instruction, otherwise it is kept as 0. So now here in this part, okay, remember that for DP instruction, this field was I field, but here it is always 0. The next bit is always 0, and these 3 bits specify one of the possible variants. So multiply instructions include multiplication with accumulation, without accumulation. Whether the multiplication produces 32-bit results or 64-bit results. Whether it's a signed multiplication or unsigned multiplication. So there are actually a group of something like 8 instructions captured by this opcode, which are represented in this manner. I've been mentioning some restriction, like in this case, R15 can't be used for any of these registers, and RD cannot be same as RM. Okay, so that's some implementation related restriction. And in the previous one also, the shift amount when you're giving by register, you can't use R15, which is PC program counter, for this purpose. I'm just highlighting this part. I think in the previous lecture I had incorrectly interchanged the position of these two. So RD is here, RN is there. Okay, the next group is DT, or data transfer instructions. Here F field is 01, and you don't have separate I bit and S bit, so there's 6 bit of opcode. RD is the destination register for load and source register for store. RN provides the base address. To that, offset is added. Now, offset could be again given in 2 different ways, but before that, let me mention that 6-bit opcode, the 6 bits are I bit, P bit, U bit, B, W, and L, and I'll not go into that again, which actually defines several variants of the data transfer instructions. The offset part could be a 12-bit unsigned constant. So unlike DP instruction, there is no rotation for the constant offset here. And it can also be a register. So if that is the case, then it is something like what you have for DP instruction, except that shift amount has to be a constant. It can't be a register. Okay. The next group is branch instructions. Here F is 1, 0, and there are 2 bits which are like opcode. So first bit is 1, second bit is called L bit. 0 means that you have a simple branch. Okay, branch could be some condition BEQ, BNE, and so on. We have discussed several of these. And L equal to 1 means that it's branch and link. Okay, so it could be branch and link if equal, branch and link if not equal, and so on. So all those conditions are applicable here also. So link, branch with link is used to make a transfer to a subroutine or a function. And the link register, which is R14, is used to save the return address. Okay. Here you have the remaining 24 bits specifying address in a PC relative manner. That means it is an offset to program counter. If you're saying you want to jump 10 instructions ahead or 4 instructions before, so it is in relation to the current instruction. Strictly speaking, this offset gets added to not the address of current instruction, but current instruction plus 8. The reason for this peculiar definition is that as the processor is implemented in a typical implementation, after getting an instruction, PC increments, and instruction execution happens in multiple cycles. So in the cycle when offset gets added, PC would have got incremented twice. Okay, so incrementation is by 4 every time because we are talking of byte addresses, and adding 4 takes you to the next word. Instructions are all full word. The data could be byte or half word or full word. So the PC would have moved on to the address of current instruction plus 8 by the time offset is added. And this offset is a word offset, not byte offset. Okay, so to get the address of the target instruction, you need to multiply it by 4 to get a byte address and do sign extension. It's a signed offset. Okay, so it allows you to jump forward as well as backward.
Sir, could you repeat this point? How the PC gets added by equals?
Yeah, so in a I think this would be appreciated much better when we come to design of the processor. But just for the sake of your curiosity, um, in a pipeline implementation, the PC normally keeps getting incremented by 4, so that it points to, in every cycle it points to next instruction. What?
Hello, sir.
Yeah.
So pipeline means like I don't understand what do you mean by pipeline when you say pipeline.
Okay, so pipeline means that execution of each instruction may take some 3, 4, or 5 cycles, but in every cycle a new instruction gets initiated. Okay, so there is an overlap. This is what is meant by pipeline implementation. So one instruction may be in its first cycle, the previous instruction has already moved to its second cycle, one before that has moved to its third cycle already, and so on. So in any clock cycle, multiple instructions are in different stages of execution. So in such an implementation, in every cycle, PC goes up by 4. And this addition of offset would be taking place in the cycle when PC has already gone up by 4 twice. Okay, so if you want to branch to, let us say, 5 instructions ahead, okay, let's say branch instruction is at some address, and you want to branch to something which is 5 instructions ahead. Okay, that means you want to skip 4 instructions and branch to the 5th one. So the address of that instruction is address of current instruction plus 20. Okay, 5 into 4. But now because of this plus 8 business, the offset you will carry with the instruction is only 12. Okay, so in the cycle when PC has already gone up by 8, you will be adding 12 as the offset, and you'll reach the instruction where you want it to. So now when you're working with assembly language, the assembler will take care of all this. Okay, what is the amount of you will say branch to a particular label. Assembler would figure out what is the correct offset required for this branch instruction. And also in, of course, high level languages, you are not looking at the addresses. You know from which statement the control is getting transferred to which statement. You may have if then else loop and so on. So the offset calculations are done by a compiler or assembler when the machine code is getting generated. Okay. Now this so all these branch instruction with different condition suffixes BEQ, BNE, etc. These are distinguished by the condition field. Okay, it's a 4-bit field, and now coming to this table which I had shown earlier. Now look at the first column. That is the value of the condition field. So if the condition field is let us say 10, in binary it will mean 1010. Then the instruction is branch if greater than equal to. Okay. So these numbers are decimal equivalent of that 4-bit pattern which you put in the condition field. Now I have been showing this condition field with various other instructions. Okay, so in fact these conditions can be applied in not just branch instruction, but with other instructions also. So we have what is called predicated execution of instructions. So if you have add instruction and you put condition with it, then it is a conditional add. Okay, so I'll show an example here. On the left you have it's a comparison of I with j, and if I is equal to j, you are doing this statement h equal to I plus j, and k equal to k minus I is being done in both cases. So I had shown earlier this example, and we looked at its machine or its assembly equivalent as shown here. So you compare R1, R2, assuming that R1 contains I, R2 contains J, and then you are having a conditional branch instruction BNE, branch if not equal to L. That means you are trying to skip this addition. Okay. So H equal to I plus J is mapped to this instruction add R3, R1, R2. R3 is containing H, and then there is a subtract instruction. So this is one way of doing it. Another way is shown here. Compare R1, R2, and you perform this addition conditionally. So add instruction with suffix EQ becomes a conditional add EQ R3 R1 R2, and then you do subtract. So you require one instruction less. Okay, is it clear? All right, assume that it is clear. Let me take another example where you have then part and else part, both are there. Again, some comparison is being done, and you either do this addition or you do this subtraction. So one way of implementing this is through branch instructions. Compare, then there is a conditional branch, perform this addition, and then unconditionally skip the first subtraction. You go to L2 straight away. Equivalently, you can get rid of these branches. You have a comparison. You do add if the result was equal, and you do subtract if the result was not equal. And then finally, this common instruction. So no branches. You can simply put conditions with add and subtract operation and achieve the same effect.
Sir, the add EQ instruction can modify the flags also, right? So in that case, it won't work.
Add EQ instruction will store the result of addition into R3 only if the previous instruction resulted in equality.
No, sir, I'm saying that in this case, it won't affect the flags. But if we give some other instruction so that it affects the flags, then the next line, the sub any, will not store the result of compare R1, R2.
Yeah, okay. That's a very good question. So the question is that what comparison instruction is doing is basically setting some value in the flags, and this add instruction is checking that. Now, question is that would the flag value still be available when you reach the subtract instruction? The answer is depending upon whether this makes any change to the flag or not. So the way I've written, it will not change the flag. I'll come to the point of when the flag changes, when it doesn't. But in this case, the value of flag remains unchanged after this add instruction. Okay. When it changes, I'll come to that in a moment. But in this case, it will not. And then therefore we are able to check the result of same comparison in this subtract also.
Excuse me, sir.
Yeah.
So in case there are multiple flags, let's say compare R1, R2, then compare R3, R4. So will it take the latest one or will it take the comparison of R1 and R2 only?
It takes the latest one.
It doesn't matter. It is between R1, R2 or something else.
Yeah. So you see, there are we are just coming to that in a moment, but there is only one set of values which you can maintain. So if you have one comparison done, and before you can check for that, you have another comparison, then the old comparison result would be lost. So now your question would be that suppose you have a complex condition like if A greater than B and C less than D, how do you do that? Okay, so even comparison can be done conditionally, right? This condition field. So you could say you have one comparison and the next comparison could be dependent upon the result of previous comparison. Okay. So or you can explicitly use you do one comparison, then branch off, and in two branches you do different comparisons. Okay, or use logical operations to combine the result of various comparisons. So there are various ways of doing it. But the key thing to remember is that if one comparison has set some values of the flag and then you do next comparison or execute any instruction which modifies the flag, then the old results are gone. Okay, so in fact the next question is which instruction modify flags. So compare and test instruction obviously modify the flag, but other instructions also can be made to modify the flag. That is up to you. You can choose. So this provision is available with all DP instructions. Okay, multiply and multiply accumulate instructions. So that entire group, you need to suffix s with that. So if you say add, instead of just add, you say add s. That means you want this add result to affect the flags. Okay, and here comes the relevance of the s field, which I have been showing. There is a 1-bit field s field, and I said we'll talk about it later. So in terms of machine code, uh, s equal to 1 means that this instruction is going to affect the flags. S equal to 0 means it's not. So the difference between add and add s is in terms of this bit. And there are instructions which you cannot make. You cannot even choose to modify the flag. DT instruction and the branch group of instruction, they don't modify the flag. So you can't have LDR followed by S. In case of compare and test, although S field is there, compare and test are part of DP instruction. Okay, out of 16 instruction, they are compare, compare negative, and test for equal. So those instructions are, as well as move, they're all part of DPs. Okay, last format I want to talk of is SWI instruction, which we have discussed earlier. It is software interrupt, and it is used to invoke some OS function. And in particular, we have been talking of using this for input output. So this also has condition possibly, and these bits are as shown. In these 24 bits, you can specify some number which could distinguish between different OS functions. Okay, for ARMSIM 2.01 version, this field is always hexadecimal 1, 2, 3, 4, 5, 6. Okay, in older versions, this is where you could specify different OS function, but in this version, it is a fixed value, and different functions are specified by contents of the registers. Okay, the would be available in the station. We'll not go into that here. Okay, so after that I'll look at some example. But if there are any questions, let me know.
Sir, I tried on my ARM sim. It is version 2.0.1, I think.
Yeah.
So like SWI 0x12345 6 was working, but SWI 0x11 was also working for exit instruction.
I see. Okay. So that may be what I understand is that the old SWI interrupts work if you enable the legacy SWI. But if
So
it
you can enable both of them in the settings. There's an option to tick both, I think.
okay, I'm not aware. So if it works, then I think there's no harm. You can use both.
Yeah, and sir, I had another question. Like in the previous slide, you just said that if you want the add and multiply functions to affect the flags, we first have s equal to 1. So is this also for the carry flag? Because like in the previous case, we saw that they affect carry flags also.
Yes, yes.
So suppose
Carry
s is 0. So
flags.
in that case,
If you want carry resulting from addition uh, to be stored in the carry flag, then S should be there. You have to say add S.
and when s is 1, so how would the other flags be affected? For example, the overflow and all these flags.
Yeah, so there are each instruction has a well-defined way in which it can affect the flags. Okay, if S is 0, it will not. But if S is 1, different instructions have a well-defined way in which they affect the flag. Okay, so which instruction, for example, the logical instruction, logical and or exclusive or etc. They don't do anything with the carry flag. Yeah, yeah, they don't affect carry flag, I think, or maybe they force it to 0. So these details one has to always check with the documentation. They don't definitely affect the V flag, okay, but they would affect 0 flag, Z flag, whereas so there is a question of, suppose you are doing addition, okay, and the second operand is being shifted. So we have talked about result of in the process of shifting, one bit goes to the carry. On the other hand, addition itself has some carry definition. So one of the two is going to override. All right. So when you want to see the effect, resulting carry from addition, when second operand is getting shifted, you need to see which carry definition overrides the other. So there'll be only one final resulting carry, and it will be either the result of addition or result of shifting. So these are finer details, fine print, and one has to be cautious. The details are always available in the document. Okay. Now let's look at an example of a recursive function. So when you're using a high-level language, you don't really have to worry about how recursion is implemented. But at assembly level, you need to explicitly provide a mechanism for recursion. Okay, so it's a function call, but you need to keep in mind that since the recursion is possible, you need to organize your arguments and data storage in a particular manner. So stack is the right mechanism for implementing recursion, and we will see that in this example. So first of all, let's have the problem definition. So this is something you know. Maze means there is a complicated structure. Some paths are there, somewhere there are blockages, and you need to find route from one point to other point. Okay, there may be as you start exploring, there may be dead ends which may not lead anywhere, and there may be some options where you reach the destination. So in fact, you have maze in real life. So there are places where such things are built just for amusement. Okay, this is a hedge maze in St. Louis, USA. Closer home, there is one 3D maze in Lucknow. This is Bhul Bhulaiya. And there are also practical scenarios where you have to solve the maze and you need computer. So, for example, a complex automated parking. It could be multi-layer, and in each layer, cars up. If you look at what happens in a plane, this is showing just a simple structure, but it could be, you could think of it as a two-dimensional matrix of parking slots where cars are parked, and there are mechanisms to park them and retrieve them. So in a large space like that, you will have to find the path of how to take the car out or how to bring it in and take it to an empty space. So there are lifts which move the cars up and down, and there are other mechanisms which move them horizontally in the 2 dimensions. So conceptually think of this, that you have a 2D matrix. Some slots are occupied by cars, and you need to, for example, suppose you were to take this car out. Okay, you need to find a way to take it out. So in steps it has to be moved. All right. Now let's try to write a program for doing that. So in step by step, you look for paths. You look in all directions and see which direction eventually become successful. Okay. So we'll do this as a recursive program, and I'm representing the structure as a 2D matrix. Okay. So a symbol B represents that this is a boundary. Okay, so these are boundary slots. 6 by 6 parking I have augmented by these boundaries, so it is now looking as 8 by 8. X represents a slot which is blocked, O is open, S is the starting point, F is the final point. Okay, so if you were to park the car here, you'll start maybe here and find a way, park it somewhere in the empty slot, or now you want it to be taken out. So from here, you need to find path to this. So either way, start to finish or finish to start, you need to find the path. So here is a recursive function which will search for the path. Okay, I'm using 2 arrays. One is maze, both are 2-dimensional arrays. So maze ij represents the I comma j slot of the maze. It could be B for boundary, X for occupied, F for finish, S for start, and so on, as I showed. And then I also maintain another array which will have 1, 0 values. So I'm calling it visited. It indicates, it marks the cell which I have visited so that I don't go over that again and again. So this recursive function, suppose you pass parameter I and j. That means you want to search from I comma j onwards. You will check if it is already visited. If it is already visited, then you don't go any further. Return is 0. That means this can't be part of the path. It has been visited and found to be useless. Okay, so return a 0 value, which is failure. And otherwise, you mark it as visited. Okay, now you are visiting it, so mark it as visited and check what is contained in this cell. If it is boundary or if it is occupied, again we can't go further, so return 0. If it is F, that means you have reached the final point, then you print the value ij and return a success. Okay, return 1. Otherwise, it is an open slot, and you can search in all the 4 directions. So obviously, if you have come to this point from somewhere, that direction you will always find visited. But in any case, for simplicity, I'm not remembering from where you have come here. So you search in all 4 directions, I plus 1 comma j, I comma j plus 1, I minus 1 comma j, and I comma j minus 1. 4 directions. And so these are 4 recursive calls. So in whichever you go through these in some order, if any of these returns a 1, you print the direction north, west, south, east, and then return success. Okay, so what you will get as an answer is that the coordinate of where you found F, and then the steps which are required to be taken to reach that point. Okay. All right, so now let's see how we can implement this in assembly language. I have rewritten this in this longish form so that it becomes easy to translate simple statement one by one. So, and also some things are simplified. For example, rather than checking visited ij equal to 1, I'm first reading this from array. Okay, that the way it will happen in assembly language. The array name will be shortened to V and M, maze and visited. Yeah, is there a question?
Sir, one thing, so here, if you're marking something as visited, then how will we backtrack? Suppose we went along a wrong direction, then we are printing, right? Then we won't be able to erase that.
Yeah, so you see, backtracking is in a way happening automatically here. You see, suppose you go in this direction and you don't get a 1, you get a 0. Okay, then this printing is not happening, and you are going to the next one. So you explore one direction. If it fails, explore next one. If it fails, explore this. If it fails, explore this. Okay. Suppose somewhere you encounter success, you get a 1. Then you print from the correct direction and return a success.
So like suppose we went along not, we always got 1 and we printed that, but then after a certain point we realized that we cannot go any further. So then
Yeah.
we need to come back, right? We need to come back, but then we've already printed the knots.
As you are printing only when a success is returned, and successful return starts from this.
Acha, got it, yes.
Starts from this point. Okay.
Yeah, got it.
So here there is no recursive call. If you reach F, then you print ij value and return success, and that would lead to multiple returns of success every time you print some direction.
This prints from finish to start. This will start printing.
So yeah. Okay, it's showing the path from finish to start.
Got it.
Yeah, one could have arranged other way also, but I'm starting from this is finish to start. Okay.
Sir.
Yeah.
So even if we find a path, then the other threads won't terminate, right? Like the other sort of branches won't close off. Like suppose if we get a path and we have another path from a intermediate cell. So then the first path would get printed, and then it would go back and then print from some other point, but not necessarily the starting point. So that would not be useful to us.
See, notice that if there is a return at this, for example, suppose this was successful. Okay. Then there is printing and return. Return means I don't even go to these statements. So moment I hit success, I don't explore further. Then there are only returns. You see.
Sir, but this won't be the shortest path, right?
No, it is not finding the shortest path. It is finding the first path. If there are multiple paths, this will find the first path going by this order. This order could have been different. It arbitrarily chosen as NWSE. Okay, so as per this order, it will find first path, and moment it finds the path, it doesn't go any further. Well, it could be, one could make it more clever, that you explore all paths, keep on tracking the distance, length of the path, and then finally select the one which is shortest. But this one is not as clever as that. Okay. All right. So our major concern is on this aspect, that how, given such an algorithm, we could have had a better one. But the question is, how do we represent or implement such an algorithm in assembly? So that's what we are focusing. So we read an array element. V is representing visited. If V is 1, then you return 0. If V is here, otherwise you are assigning 1 to V and then proceeding forward. So the way it happens in assembly, reading and writing, loading and storing are separated. So that's why I have split these instructions. So Q we will implement with a register. Q gets this, and then we are comparing it with various values. Okay, here you have recursive calls. So now there are two parameters, I and j. We are passing these through R0 and R1. Okay, and we are pushing various things in the stack, as you can see. First is that we need to save the link address. Link register is saved on the stack, and that is very essential for a recursive call. Otherwise, you would lose the track of where you came from. All right. Link register has information about where you need to return, and that we are storing in stack. So this is a pre-decrement. Okay, this is auto indexing, pre-indexing, and it is decrementing. So SP is decremented by 4 first, and then at that address you store LR value. So I'm assuming that SP points to the top filled location, and therefore for pushing you first need to decrement stack pointer and then store something there. So R0, R1 are also saved. Now we want to load ijth element of array V. So now how do we handle 2D matrix? We take I value, which is in R0, multiply it by 8 by logical shift left 3, and add it to J. So what we are doing, basically J plus 8I. Okay, because it's 8 by 8 array. So with relative to the base of the array, the address of Vij is 8 times I plus j. Okay, is it clear? So R1
Could you explain it again?
Yeah, you see, we are talking of this 8 by 8 array. All right, like this. So suppose I is 0, 1, 2, and j is 0, 1, 2, 3. So we are talking of, let's say, this element. Okay, I is 2, j is 3. So what is the address of this? It is 0, 1, 2, 3 up to 7. Then this is 15, 16, 17, 18, 19. And how do we get that? It is 8 times 2 plus 3. Okay, I multiplied by 8, the dimension of the array, or let's say length of the row. To that we add j value. This is what is happening here. R1 plus 8 times R0. That is in R2. So R2 has the offset. In R3, you load the starting address of the array, and then you load a byte. So I'm assuming that 1 byte is used for each element of the array. Okay, each element just requires 1 character to be stored. So we are not using full word, we are using a byte. And then we can do LDRB. So R4 has a small v value. R4 corresponds to small v. R3 as base, R2 as the offset.
Sir,
Yeah.
so here a word is equal to a byte, right? Because we have only one character. So why do we write B?
So each array element is 1 byte in this case.
Hmm.
Okay, so we just want to read one array element, which is 1 byte.
Yes, sir, but here the word doesn't consist of anything else, just that byte only, B or X or O.
So okay, so this matrix will be stored in 64 8 by 8 is 64 bytes. That is 16 words.
Okay, got it. Got it. So then if we did LDR only, then what would we load?
Then 4 bytes will come.
Acha, okay.
4 bytes will come. So it's not a huge array, it's a small array. We could have actually afforded 1 word per element. It's not too large. But if it is large, then you'll try to save space. So if byte is sufficient, you'll use just 1 byte. Okay, next
So the
comparing. Yeah.
so the store LR store R0 store R1 they automatically increment the stack pointer as well.
Yeah, here this exclamation you see, this means that SP gets modified by this instruction. The base register, which is SP or stack pointer, that will get
Okay.
modified. So SP will become
So
SP
the stack
minus 4.
so the
Yeah.
stack pointer is from maximum to 0, not 0 to maximum.
Yeah, stack pointer is stack is growing towards lower addresses, towards 0. Okay, next we are comparing v, small v, which is R4 with 1. And if it is equal, we want to return 0. So I'm only saying branch if equal to RET0. RET0 is a label where we will return a 0 value. Otherwise, we are storing 1 in Vij. So move 1 to R4 and store byte. Oh, by the way, these V values are 0, 1. We could have actually packed it even further. Stored, just use 1 bit per element. The other array is array of characters, so there we need a byte, but here we could have used even, we could have compressed it further, have 1 bit per element, but I've just kept it a byte array for both cases. So we are storing this constant 1 into same address, R3, R2. The general picture about use of stack in function calls is that with every call you use up some space on the stack. That is called activation record or stack frame. And it so this I'm showing part of the stack here. I'm showing just one frame or one activation record, and the stack pointer is here. So with every call, some space like this will get put on the top of the stack. And when you return from function call, that much is popped off. So depending upon the nature of the function, you may have various things stored on this. So you could have parameters. Notice that some parameters can be passed through register, but if you have many, then the remaining get passed through stack. Then you have return address, and then you have some local data for the function. So function may have some local data space, which is allocated again on the stack. And when you come out of the function, all this gets deallocated. Okay.
Sir?
Yeah.
So could you repeat what is the significance of the exclamation mark in the LDR?
Okay. Significance of exclamation mark here in these structure is that the computed address is stored back in the register. Okay, if you don't have exclamation mark, this subtraction is still done. Okay, you will do, you will compute the value of SP minus 4, use it for memory access, but not store it in SP. Okay, so with the exclamation mark, state of this register gets modified. Okay, so two modification take place. One is data transfer between memory and register, and other is the pointer update. So if exclamation is not there, pointer will not be updated.
All right, sir. Thank you.
Okay, the next step was we are now reading one element of the maze. So R3 is the base address. R2 still has that 8i plus j. So load a byte from there. Check if it is B. Okay, if it is B, then return a 0. So B EQ return. Then checking if it is X. If that is the case, again return 0. Otherwise, if it is F, then you need to return a 1. So if it is not equal at this stage, then you are going further to label L1. Otherwise, you are printing. So in R0, I'm loading this character 0. So value of I needs to be printed. So I is a number. To that, let's say okay. So I'm printing the value of I as a character. Okay. So code of 0. To that, I'm adding this number. So it will be, suppose I was 3. Okay. So you add number 3 to code of 0, you get code of 3, and that code is getting printed. So I'm printing this as a character. Similarly, print J. Okay, R1 has the J value, so print that, and then return to 1. So for that, I'm saying branch to RET1. So these have not yet been defined. These labels RET0 and RET1 are coming further down. Okay, so now the crucial thing, a recursive call. We are making a call to search function with I plus 1 comma j. So now by now I might have modified R0 R1 register. Okay, I would have played around with those used for printing and whatever. So I need to get these back from the stack. So I get R0 R1 back from the stack. These are pop. Okay. Here at incrementing I by 1 and making a recursive call. So you see how it is happening. This is whatever is on the top of the stack got into R1. and what is one step down, one location down, is brought into R0. So I've not modified SP here. So these values are taken off, but not removed yet. So they are still in the stack. And a recursive call is made. As you remember, as we entered the function, we saved the value of R0, R1. The parameters IG are saved. So the new values will be saved as you enter. The stack will build up. Only when you make returns, the popping is done. So here SP is not modified. Two values are read from the top. Now, from this call, the control will come back here. And the value is being returned in R0. That is the convention I'm using. Okay. So at high level, I'm saying P gets search I comma I plus 1 comma j. In assembly, a true false value will come back in R0. The assumption I have. That is being compared with 1. And if it is not 1, then I need to make next recursive call. Okay. Otherwise, if it is 1, then I'll be coming here. I'll print a value of n and return a success. Okay. So L2 at L2 there'll be next recursive call and so on. Now let's look at the return. How I return true or false result and how the stack is popped. So the result is being returned in R0. Okay, I need to return 0. So return it in R0. Load this value in R0, and then retrieve the return address. Okay, where was the return address? It was at offset 8 from SP. So let's go back and see that picture. See the order in which we have stored things. First thing we pushed on the stack was LR. Next thing we pushed was R0. Next we pushed was R1. Okay, so R1 is on the top. Next is R0. Next is LR. So LR is at 8 offset below the top. Okay. And while as I'm returning, I don't need to retrieve R0, R1 anymore. Okay, so I simply need to adjust the stack pointer value. So add 12 to that because three words were pushed in the stack, and now it is like removing those 3. Okay, stack pointer is brought down by 3 position or 12 in terms of byte addresses. So now LR has the return address. I can simply say move PC comma LR, and that takes care of return. Now,
Excuse me, sir.
Yeah.
Sir, the answers are stored in the register side R0 and R4. So R1.
The input parameters are coming through R0, R1.
Okay.
The result is going back using R0.
So when we call ret 0, let's say, or ret 1, so what do? We store something in LR. What do we do when we call ret 0?
We are not calling ret 0. We made a branch to this.
Yeah, that's it.
Yeah, there was a branch because from many points I'm returning a 0 value. So,
so what actually happens when we return a 0 value?
Yeah, so the control is getting returned at this point when you say move PCLR. Before we do that, we need to retrieve the return address from the stack, because every time you make a call, PC value gets saved in LR, and then we are pushing it. Saving in LR is automatic, but LR has to be saved further in the stack. That we are doing explicitly.
Okay, so does LR always return the value of R0?
No. LR is the return address where, see, in the program, let us say here. Okay, here is, for example, one recursive call. You're doing BL search. After doing one execution of search, the control returns to this instruction, the next one. So from this point, it goes to search, does all that, and you come back here. How you come back here is by virtue of LR, because moment you say BL search, the address of this instruction is saved in LR. But since they are before I return, there may be further recursive calls made. You need to keep saving the return addresses. So let me take it to the C program, which I had written. See, now you have search function starting here, but within this you have multiple recursive calls. Okay, so what is happening at assembly level now? Try to visualize. When you are making a call here, the control is getting transferred here. So it will go through all this, and when return happens, it should come back to the instruction which is after this. Okay.
Okay, fine. Thank you.
So every time you make a recursive call, every time you call, let's say when you say BL search, LR value gets modified. So if LR at that point was containing some return address, that will be lost. So therefore, there is a need to save it, and we are saving it. So as soon as you enter search, you don't know from where it came. That information is there in LR. You save it in the stack, and also save R0, R1, because in the process their value may get modified, and you need R0, R1 again to prepare the next set of parameters, because you may be making a call with I1 plus I plus 1 comma j, or I comma j plus 1. So you need ij values when you're making this. Yeah. So here we are retrieving R0, R1 from the stack. We are not popping them off. They are still sitting there because you might need again for next call. So you get these from the stack. R0 contains I, you are getting I plus 1, J is as it is, and you are making the next call. Okay. Similarly, you will make 3 other calls with slightly different values of I and J. So the purpose of saving I and J is visible here. And the purpose of saving LR can be seen here, that you need to retrieve LR and return the control. Okay, this part return one is very similar.
Sir,
You move one in. Yes, please.
sir, like then suppose we have any kind of function, then we'll always write this line that we'll store the, we'll get the, I mean the address from the stack, the top of the stack.
Yeah, to support nested calls and recursive calls, uh, you the practice is to save LR in the stack, and just before returning, retrieve it and use it.
But so like in general, when we were writing the GCD function, we were not doing this. It was done automatically. We were just writing move PCLR. But then here, since we're making calls to the same function.
If there are no nested calls, then it is safe. You can leave LR as it is.
Acha. Okay.
Yeah. See, if there's only one level of call, you have main and you have a set of functions. No one calls each other. Only main call each function. Then it is safe. You see, LR will not get overwritten by another call.
Okay, sir.
Okay. Yeah. So that sort of completes the program. There are some repetitive parts which I have not shown. So here you can declare your M and V array. V I am initializing to all zeros. So we had 64 bytes, which means 16 words. So I'm initializing all 16 words as zero. M can be initialized by .ascii. So it's like a string, you know. These are 8 B's which correspond to the top row. The next row is this and so on. Okay, so that's about the program. And for this example, if you run, suppose you had started from this point and you had F here. So it'll reach this point, find that F is there, and then retrieve the path. You know, the sequence will be printed as follows: 4 and 3. 4 comma 3 is the coordinate of this. And then south, east, north, 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 west, west, northwest. Okay, so in context of this parking, if you were to retrieve this car, so you can trace path from the gate, from the starting point to this point, or vice versa, depending upon how you have written the program. But actual situation could be more complex. Now, how do you retrieve a car like this? There's no path, so you need to create paths by moving other cars, and this is what complicates the problem. But this is how it is done in such a scenario. You would need to shift a few other cars and create a path. So what is the minimum amount of shifting you need to do? That needs a somewhat complex algorithm. Okay, I want to stop here. If you have any further questions, I can take those up. Your first assignment will be announced today. That will also, what I'm planning to give you is writing function for merge sort in a recursive manner. Okay, so merge sort, I'm sure you are all familiar. If you have to sort an array, break it into 2 parts, sort each one, and then merge the 2. So sorting each part means you make a recursive call. Okay, so you can keep breaking till you reach a point where the sorting is trivial. You have a single element left, and we'll do this for sorting an array of text, array of strings. All right, so you'll start to begin with. You'll write small just to get warmed up. First part would be to write a function to compare two strings. Okay, then write function to merge two sequences of strings, and then put all together to build a merge sort program.
Sir,
Yeah.
strings are stored in so strings are stored in the stack and like they'll be of variable length, right? So it will be
Yes.
a bit
Variable.
weird.
Yes. Yeah.
Okay. So excellent.
Any question? So I'll write it down properly and it will get announced today.
Sir,
Yeah.
so the process of storing strings in the memory would be of this form, right? Like the first register would specify the length, and then we would have characters. We would have bytes of characters.
What we will do is we will assume strings to be null terminated.
Okay.
Each character is 8-bit character, and the code consisting of all zeros indicates null. So variable length strings are typically stored in this manner, that you have that indicates end of the string.
Okay, sir.
Sir,
So you will, yeah.
so the two kinds of input that you had said with the legacy on and legacy off, which one should be used and like in which what situation? They were giving two different outputs.
They give different outputs.
Also, like when we keep it off, then we don't get the. In case of integer, we get an output, but in case of not integer, we are not getting an output. Something like that. I've forgotten. Somebody had posted on Piazza. I was also facing the same thing.
So I have not tried myself, but my understanding is that if you if you enable legacy SWI function, then the old ones can be used. If you don't, then they cannot be used, and you have to use new ones. So you can possibly stick to one to avoid any confusion. Either use the new calls or old calls.
Okay, sir.
Yeah, when it comes to storage of bytes, then you need to be careful about which order is being followed. So within a word, there are 4 bytes. But are they numbered left to right or right to left? Whether it is big endian or left or little endian. Okay, so these things could be implementation specific. So in your implementation, you would need to check whether which one is. Otherwise, the interpretation could go wrong. Okay, so you have byte 0, 1, 2, 3. Does it go from left to right or right to left? So that you will have to see. Okay, I'll stop at this.